Welcome to Team C3's Demo 2 presentation. You can now see on your screen each team member's roles for this demo, with little change from the last one.
Here we have the final design for the line following robot. The chassis is entirely comprised of custom designed 3D printed parts. This allows for a higher degree of adjustability and modularity. The final iteration of the design is dramatically shorter and has also received a thinner wheelbase than the first iterations. This allows for a tighter turning circle and for the robot to stay on track better.
To detect the start and stop section, an ADC sensor detected every black line and would increment the counter to know when to stop. For the slow zone, another ADC sensor detected the varying values and would cause the robot to slow down or speed up when it detected the specific color value. To detect corners and straights, some modular code was implemented that detected if it was in a corner or on a straight depending on if it had odd or even in its banks, toggling the LED appropriately to be turned on the straights. There was much inconsistency with the sensor detection, so debouncing and a sensor light shield was implemented to counter this.
One of the major updates on the robot was the implementation of a PID controller to dynamically adjust its trajectory to follow the line. Error for the PID controller was calculated as a weighted average of car's position relative to the center of the line. To adjust, the PID controller had a proportional term Kp, which proportionally varied the steering angle based on the current error. Proportionally controlling a car's steering angle with sharp turns, however, could lead to an oscillation state, which can be accounted for by predicting the next steering angle, the derivative term Kd, and accounting for it at the current state. Finally, with active mechanical components, any mechanical defects could lead to a steady state error. In line following, the integral term Ki accounts for this by monitoring the error history and adjusting to return to the center of the line. The PID gains were tuned using a combination of Ziegler-Nicholas method and empirical tuning methods.
For the bonus feature, a Bluetooth module was implemented to significantly extend the capabilities of the line follower. This was connected on an onboard breadboard to the Spark serial receive and transmit pin, which demonstrated the feasibility of a live debug and status update, as well as remote control.
The project plan was followed closely, with steady advancements made in each sprint, as you can see with the backlog broken up for each sprint. Sprint 1 consisting of the initial construction of the robot and basic code for each component. Sprint 2 added working sensors and more advanced code to control the robot. Sprint 3 was the implementation of the sensors with PID following the line and side sensors for flags. Sprint 4 was the fine-tuning of the sensors and implementing a Bluetooth module.
Here is the final budget for our project. Since the last demo, multiple 3D printed parts were added, including the V2 chassis along with front and side sensor shields. Along with this, a Bluetooth module was purchased for our bonus feature.
Demo 2 consisted of 2 sprints where various independent work were done by each member before combining towards the end, where we discovered that combining all components took longer than expected. The excess time can also be seen in the backlog below. The overall burn down chart and the backlog can be seen below, and the effects of excess time on Demo 2 is significant. As seen, there was an inconsistent work output, which led us to not being able to seek external guidance effectively and early. This highly likely led us to the higher debugging times. Nevertheless, team communication was excellent, and combined with the variety of skill sets in the group, the cooperation has led to a high quality product.